All right, guys, gonna get started. Thank you all for coming. It's great to be here. It's actually my second time at Scala Days. I attended New York last year, and I'm here in Chicago today. So we're gonna be talking about a lot of cool technologies, Akka, Kafka, Spark. So it should be a pretty good time. We have a lot to cover, so let's get started. But before, just a couple of things. I just want to let you guys know who I am. I work at Pluralsight, data platform architect at Pluralsight. Been there for a couple of years. Before that, I worked at Rackspace. 4 or 5 years doing Hadoop, data systems, data engineering, that kind of stuff. And before that, at Disney World in Orlando, Florida. And I want to spend some time as well talking about Pluralsight because it's relevant to the conversation that we're going to be having today. So Pluralsight, for you guys who do not know about Pluralsight, is an online technology learning platform. It is subscription-based, meaning that users go and pay out a flat fee every month, and they have access to a huge catalog of courses, all technical stuff. And it's a very data-driven platform in the sense that we collect a lot of data, and we also use that data to make the product, to make the courses and the user experience better. And it's a very microservice-centered architecture, and that's kind of some of the topics that we're going to be talking about today. So what are we going to be covering today during this talk? Like I said, it's quite a wide range of subjects, but I'm going to try to cover everything, and then we can save questions for later towards the end. So we're going to start with microservices, a little bit about that, architectural design decisions. We're going to go talk about databases, relational architecture, what some features of databases that makes them so compelling for users today. We're going to skip over to commit logs, talk about Kafka, what is a log, what's a distributed commit protocol, talk about ingestion, best practices to ingest data in real time, and talk about Spark and stream processing in general. And then at the end, we're going to try to tie all this together into a cohesive model of how to use stream processing to bootstrap a microservice, in summary. All right, so microservices, we're going to start there. I'm sure we all have seen this picture or some form of it, of a monolithic application. This is probably back in the day of, what, J2EE, Tomcat, WebSphere, massive WAR files, 100 megabytes, night-long deployments, and everything is basically this massive monster. Everything gets deployed together. The teams are big teams talking to a centralized database. And you can compare this with the microservice approach that you're pretty much splitting that monolith into many processes, right? Different code bases, different GitHub repositories, different CI pipelines. And since the focus of this talk is really about data, you can also see that each microservice has its own data structure as part of its bounded context, which is an important thing to talk about. And this is just another way to talk about microservices and monolithic services. And most people seem to resonate with this pretty well. So there you go. All right, so why do we do microservices? First one, I mean, there's just this innate desire of death to the monolith, right? I mean, like I said, if you ever have to stay up all night deploying this WAR file to Tomcat or WebSphere and it doesn't work, you don't want to do it anymore. So that's number one. And then number two, autonomy, right? There's a lot of value in have services who are autonomous. But if you really think about microservices and the big drive, the big push behind it, it's about independence. And independence comes in two different realms. There's different ways to talk about independence. We're talking about services that can be independently built from each other. They can be independently testable. If I'm testing my service, I should not be breaking anything else. I can test my service in isolation. We're talking about things that can be independently deployed, like we saw with different CI pipelines. And there's also two ideas that I want to talk about. They're not as tangible as the ones that I just brought up. And one of them is about teams. Microservice allows the organizations really to grow because the teams are small, cross-functional, and they own the entire development lifecycle for that specific piece of the product. And then number two is data. Microservices are meant to be data independent, but it's hard. That is the hard problem that we haven't really solved yet with microservices, and that's kind of the whole point of this talk is to really focus on that layer, on the data sharing layer. Because it kind of looks like this, right? I mean, microservices are meant to exist in isolation, be isolated. I mean, the other way around. Microservices are meant to be isolated, but they don't exist in isolation, right? I mean, you're sharing data, you're producing data and maybe to a message queue, and that boundary becomes really, really fuzzy because most services kind of slice and dice or work with the same core business entities. They kind of share somewhere in between. It's very unlikely that you will find a service that has such a tightly bounded context that making changes to its data set is not going to affect anybody else. It's usually a very tight dependency net. And you have things in between like a message queue, rabbit, 0MQ. That's kind of how we do that now. And that kind of brings the question, right? I mean, what data do we share? What data do we have to share? Do we need to share? And how do we do it? And it's really, at the end of the day, it's about this. It's about this mismatch, that you have a service that's trying to encapsulate and loose couple as much as it can of its data internally, and only basically showing things at an interface layer. And you have all the other services that depend on that service wanting something completely different. They want a much richer data set that they can relate to, that can navigate, that makes sense to them. And you as a service provider, you cannot, it's very extremely hard to be able to fulfill the data requirements for all the services that depend on you. So you end up with a generic layer of data that you think everybody's going to need, but then something like this happens. You have all the other services that depend on you basically creating their own copies of your data. And because of this, they get out of sync. And over time, data will diverge. So is there a better approach, right? I truly believe there is, and this is what we're going to be talking about today. But before we do that, let's take a little side step and talk about databases, because databases are the kind of the status quo for data systems and services today still. And part of it is just inertia, right? I mean, they have been around for a long time. A lot of tools. You have Oracle, you have these massive players in the industry who do databases, so we use them. But if we were to unbundle or split the database into different components, what are some of the features of a database that we want to bring into this new system that we're talking about? So transactions being one of them, right? I mean, we all know transactions, and they're very powerful, though they're probably overused today, but they're powerful. The idea of having these multiple operations appear as if they were running as an atomic unit, rollback, commits, I mean, that's really powerful stuff. It's a really good feature of databases, but it's also kind of old school, especially if you talk about distributed systems and Spark and all these other stuff. That's not really relevant, right? There's other ways to do it. And I challenge you guys when you go back to work next week, right? I mean, look at your systems, look at your services, and ask this question. Look at your database layer, look at your service layers, and basically be like, hey, what consistency do we need? And most importantly, when do we need it? And I think you will probably find that for a lot of use cases, you don't need that kind of strong consistency that we're used to. Eventual consistency is fine, or no consistency at all might be okay if it's just an event system, I don't know. But it's interesting exercise that we have been through, and we actually found out that we're applying a very strict, a very strong model to things that did not need that overhead. And there's also this concept of Asset 2.0. I'm not going to spend a lot of time here, but this is more about, you can look it up. It's definitely worth the read. It's the same acronym, ASSET, right? But the words, the letters mean something different, and really applies more towards this kind of distributed environments that we're talking about, like the eventual consistency models that I'm bringing up. Okay, so feature number 2 that databases do and do really well, indexing. I mean, we all know a primary key, a foreign key, or even index on a column, right? I mean, they're really cool. And I had a hard time trying to find out like a slide to explain what indexes were. So I was talking to Dustin yesterday, who I have the honor to work with, and this is a direct quote from him, and I think it's pretty good. I mean, take a couple of seconds to read it. But yeah, it's about looking up things really fast, right? So you don't have to scan the entire table if you don't need to. So it's an awesome feature. Maybe it doesn't really belong in a database because it puts a lot of load, a lot of overhead in a database. But forget about that for a second and just having an index. That's a pretty awesome feature to have if you are a service. The other one to talk about is replication, just like data replication. We're pretty familiar with this. Like, I mean, most databases do this today. And the idea is that you have a leader that replicates data, sends data to all its followers. And it's really about failover and resiliency, in the sense that if a leader fails, anybody else who's following that leader should be able to pick it up and take it from there. In theory, right? I mean, sometimes it doesn't happen that way, but that's what they say. And really, the point that I want to bring home here about replication is this, right? There's a major difference here between a state mutation, an imperative state mutation. That's kind of what we do with databases. If you're trying to update a row, a record, you just basically issue an update statement. And then the whole record changes, right? I mean, you lose history, unless it's a data warehouse, but let's not talking about that right now. Just you change the record, you lose the history, whatever the state was before that point in time, as opposed to sending a immutable fact, which is what we see at the bottom, right? Here, we're basically saying at 2:39 p.m., user 121 did this. And that's always true. It doesn't matter what happened before, what happened after. At 2:39 p.m., this happened. And you see a lot of this paradigm, a lot of this design shift with event sourcing. And it's really important for bootstrapping. If we're talking about stream processing and bootstrapping and Kafka, that is the paradigm that we want to shift to. We don't want to do the first one. That doesn't work. We want to make sure that we have an immutable event stream that we can replay events from. And then the last feature of databases that's worth mentioning are views. I'm not going to spend a lot of time here, but we have this idea of virtual view that basically gets compiled, gets rewritten, reinterpreted every time that you run the query. There's no materialization. There's no actual space, physical space being taken. And there's also a materialized view that the database goes behind the scenes and materializes the results of that query, the view, into its own table space. And it also does some magic behind the scenes to try to keep that up to date. And again, it's a great idea, but does that belong in a database? That's the question, right? Because again, it puts a lot of overhead in something that should be pretty simple, should be just storing records. So is there a better way? Again, posing that same question, right? So what if we could do something like this? What if these are all services, the little colorful boxes, they're all services. In the center, you have a commit log. So here, let's say that we have a user service, a user microservice that does user stuff, and it owns the user datasets, the user entities. And every time there's a transaction, there's some type of operation, an event, it writes that to a commit log. And then everybody else, there's a streaming processing framework that's continuously streaming or replicating those events back to the other services who need it in a way that makes the most sense to them. So the shared state is only in the cache in each service. So those become local caches of data. The truth is in the commit log. Everything else is just different ways to represent that same log through a streaming processing framework. And if you do it like this, since the shared state is only in the cache, data will not diverge. So let's talk about the log, right? What's the commit log? And for this, we're basically going to talk about Kafka. It's going to be a very specific conversation about Kafka, but it applies to other commit log systems as well. So if you were to talk about Kafka in one sentence, we could just basically define Kafka as being a messaging system that's based on distributed logging semantics, right? So it's scalable because the brokers, the logs can be replicated across different brokers. It's fault tolerant for the same reason because of replication. It's stateful, the logs are always there. And there's also a explicit, strong ordering mechanism within Kafka itself in the sense that the messages will be given to the consumers in the order in which they were received. That's unique for a topic in a partition, so global ordering is a separate subject, but the idea is that Kafka has strong ordering semantics within a topic in a partition. In high concurrency, from the get-go, there's some very interesting engineering tricks within Kafka itself to make sure that it can service thousands of requests concurrently, both from a production side and a consumption side. And internally, Kafka does have a replication protocol. So every message that gets sent to Kafka has a key and a value. And there's only one leader. So even though there's a massive cluster behind the scenes, every message goes to one leader. And that depends on the topic and the partition. But the idea is that after the leader gets the message, it gets replicated to the followers, and then the consumer, the producer gets an acknowledgement saying, hey, I got it. And it's really about resiliency, right? I mean, the whole replication protocol in Kafka is to make sure that Kafka is fault tolerant, and if a broker dies, everything is okay. We get a notification, put it back up, but the message consumption and production should not be altered. And even though there's all this stuff behind the scenes, guys, it looks to the outside like a globally ordered queue. Very much, you could use this like 0MQ or a RabbitMQ, you could, even though that's just the tip of the iceberg. If you're using a simple consumer in Kafka, that's kind of what it looks like a queue. So let's talk about the log, because that's kind of the whole point of this distributed commits, right? So you can think about log logically as a file. It's very much like a file. It's a linear structure. The messages come in, they get appended at the end of the log, at the head. And consumers have a position within that log. It's an offset-based position. There's no random access. You basically scan to an offset, and you go from that point on. Now, the cool thing that makes Kafka really special for these use cases that we're talking about today is that messages can be replayed, in the sense that when a consumer consumes a message from the topic, it doesn't get deleted. It's always there. So I can come back later and replay the topic, replay the log again. And because of that, we can use Kafka as a distributed replication protocol engine, because we can do the rewind and replay for as long as the messages are present in the log. So this is something we should talk about as well, right? I mean, how long are messages present in the log? Because that's kind of the whole point. So can you make Kafka hold logs and messages forever? Yes, you could. Though I have changing configuration parameters. Though I have not ever seen that done in production. It's usually one of these two policies that we're going to talk about. So the first one is the delete policy. It basically says, hey, after the log reaches a certain size, or after a certain period of time, every message who's older than that threshold will just be dropped. So the log always stays at a constant size. And then the other one that really applies for what we're talking about today is the compaction. So log compaction, like I just talked before, if you guys remember, Kafka messages have a key and a value. And what compaction does, it guarantees that every message in the log will be present for a given key. So the latest version, at least, the latest version of every message in the log will be present for a given key. So the older ones will just get dropped, and Kafka just basically keeps the latest snapshot of a message given a key. So it's pretty good, because if you're talking about bootstrapping, you don't have to replay this massive log. You basically, because it's a lot compacted, you only have to replay the latest version of each message in the log. So, all right, so now we can go and talk about stream processing. And I think a good way to talk about stream processing is drawing a comparison with what we're used to, like the finite, discrete database type of processing. So if you have a database query, a select query, you go select star from table. It takes a while, possibly, and then you get back a result set, and that's it. Your relationship with the database is over there, in a way, right? I mean, if you want to update that result set, you have to go through that entire process again. As opposed to a stream processing framework, that you have these continuously updating data sets. They're always being updated. And it's usually over a window of time, over a day or over 2 seconds. There's usually some type of window aggregation that happens there. And in terms of features, most stream processing frameworks do support very similar features to a database. You can do stuff like aggregations, you can do filterings, you can do views, you can do joins, exactly the same, very similar. There is a bunch of different streaming platforms, I would say four of most of the prominent ones right now, streaming platforms that you could choose from. And here they are. We have Kafka Streams, which is part of the Kafka distribution. We have Akka Streams. We have Spark Streaming and Apache Flink. And even though, so truth be told, there's a lot of overlap. So the Akka and Kafka Streams are the most lightweight ones. They're very lightweight. They don't need a cluster to run. Spark and Flink are the most robust. And there's a lot of overlap between these frameworks. And it really comes down to two major points, which are latency, meaning how close to real time do you want your stream processing to be? Do you want it to be like milliseconds or microseconds or exactly at the same time the event happens? Or can you tolerate a second-based latency? And then the second one that you need to think about is the size of your result sets, I mean your data sets. Kafka streaming it's good because it's lightweight, but it doesn't really support a lot of joins or massive data sets. Spark streaming, on the other hand, is really built for that, right? I mean, it's a workhorse. You can just dump massive gigabytes of data into Spark, and it's going to do just fine. So a lot of choices, right? I mean, we had, and we decided for us, for our data platform Pluralsight right now, we decided our first implementation of streaming would be Spark. And these are the reasons why I'm going to talk about them a little bit, because it's an interesting discussion. This is actually an active discussion that we're still having right now. And the idea is to ideally we'll be able to support different frameworks. But the reality is that the data platform that we're building is meant to serve a wide variety of use cases, right? I mean, bootstrapping being just one of them. We have data scientists, we have data engineers, and we want them to use the same streaming backend that we have. If we use Spark, we can basically all use the same API. right? Because it's just data sets, just data frames or RDDs. And they can basically leverage our APIs that we're building to do this, to do some more type of processing, to do like machine learning or graph processing within Spark, because Spark has that. So for us, that was one of the major things that we looked at. Spark is more user-friendly for them than any other one of these tools that are out there, because Spark has the REPL, it's just easier to use, and there's this unified API. And number two, because again, this is also a data engineering product, data engineering doesn't work with Kafka only. There's a lot of different formats within Pluralsight. There's CSV files, there's JSON payloads, there's Avro, there's Cassandra, and we want something that we're able to connect all these data sources to put data into Kafka as well. And Spark has that functionality already built in. I mean, if you go to the Spark code base, there's Elasticsearch connectors, there's JSON, there's Avro, so it's already there. So we don't have to write that. And that allows us to kind of stay at a level above as opposed to having to write connectors for all these different systems that we have today. There's also structured streaming as part of Spark 2. And that allows us, that's a pretty cool feature, and that allows us to, because the system that we want, that we're building, we wanted to be able to handle both streaming processing and batch processing. And that's what structured streaming does. You can basically switch from one to the other, like without, it's just changing one parameter. And then we also have the failover and lifecycle management that we get from the Spark cluster itself, which is pretty important, especially for microservices, right? I mean, if your database is down or if Kafka is down, you don't want the job just to kill and stop running forever. So Spark provides a lot of that. And again, we just don't want to deal with that right now. Spark does it. And we were OK for bootstrapping with a medium latency. We're OK with seconds. We don't have, it doesn't have to be a millisecond delay, right? I mean, we're OK waiting a second or two for data to be materialized all the way from Kafka to another service. So if you take Spark into the picture, if you put Spark into the picture, that's kind of what it looks like today. So we have these different services that write to this event stream, and this is Kafka, to the log. And then Spark, there's a bunch of Spark streaming jobs, or even just Spark core jobs running behind the scenes that will replicate that data, those topics, join them, filter them into Hadoop, HDFS, or running ETL jobs, or bootstrapping those to other microservices. That's what the service, that's what it means, is that's the bootstrapping. And the transformation box, the last database thing, is actually talking about running transformations from Kafka within the Spark itself and pushing those back to Kafka as derived topics. And a derived topic in Kafka or in a log basically means, let's say that you have two raw data topics that you're aggregating, and you're using Spark to do that over a window of time. And then we push that back to Kafka so that anybody who's interested in those aggregations can just listen to the derived topic itself. Does that make sense? The derived, okay. So how are we doing that internally? And this is more specific now. So now we have the concept to kind of know what a log is and stream processing and why we're using Spark. So how are we doing this? So one of the first things that we did from the beginning was to be really clear about the separation of data capture or data ingestion from data replication. We actually have them as completely different code bases. Because the idea is that if you can get data into Kafka, into the platform, then this all colorful world, right, opens to you. So that's the first step for anybody who wants to use the platform. We have to tell them, hey, the first thing that you need to do is to get data. You need to get data into the platform. And we're trying to make that as easy as possible, and I'm going to go over that. And that's the idea. So the replication into other services, into other streams, or back into Kafka, it happens after the fact. It is an afterthought. And it's actually by design because we want to be able to separate these two processes from each other. We want them to be independent from each other. And internally, we're using this. It's a data replication platform. It's called Hydra. That's kind of like the code name. And I'm going to talk about it a little bit, going to kind of some of the design decisions that we made. And it's open source. It's not, we're going to open source it. There's part of Hydra is already open source, and I'll get there and I'll talk about it. But it's really, Hydra is really about replication of data, right? And Kafka is mostly just a data system that Hydra uses. It can pretty much use anything. And like I talked about, there's two modules within Hydra right now. There's the ingestion module, and there's the streaming module that we're going to talk about, the Spark-specific module that we're going to talk about in a little bit. And Hydra also has an ingestion protocol. right? So there's basically a request that comes in, and that request is a combination of a payload, mostly JSON, because that's the majority of our use cases right now, just JSON, and some metadata attached to that payload that describes that request somehow. For instance, if it's supposed to go to Kafka, maybe the name of a Kafka topic. If it's supposed to be retried, if it fails, the name, like a retry strategy. And then what Hydra does, it goes, and this is Akka, by the way, right? So I actually kind of want to talk about that as well. So Hydra is written in Scala, and it's 100% Akka. So it's basically an Akka application. All of these ingesters and transports that we're talking about, they're Akka actors. They're specializations of Akka actors. And the idea is that we have routers and we have location transparency across all of this, that when a request comes in, it gets broadcasted to all the registered ingesters, and they basically have a chance to analyze the request as it comes in and see if they're interested in doing something with that request or not. And that's what the metadata layer does, like with the request. And then if they are interested, they basically send that request as a record now, as a Hydra record, to the transports. And what the transports do, they will actually send that data, will replicate that data to the underlying data systems. Right now, we have a Kafka implementation, right? So that's the default implementation. So there's a Kafka transport within Hydra, and that's how we get data from the outside, from other services, into Kafka, through this framework. But we could also have and that's the idea, right? I mean, to have a Postgres transport, or a database or Elasticsearch transport, that will be able to replicate that data in real time as it's coming in through these different systems as well. And like I said, they're all actors, and the idea is that they can either be deployed within the major process, within the Hydra process, or they can be completely remote actor systems. Because Akka and the whole location transparency and remoting, we can do that. We actually have some use cases now to consume messages from like Rabbit. That's what we're doing. They're ingesters that are remote. They don't run as part of the major Hydra code base, but they also kind of follow the same protocol. And then, so that's kind of what it looks like. The ingester, I don't know if you guys can see that, but I just wanted to show you, like that's what basically the ingester code base. And the reason why I brought this up here on the screen is just to show you, like that's the publish that I talked about before. It's actually a message that gets sent by a supervisor. And that gives everybody who is an ingester the capability to either accept that request or not. So what we're doing here, we're building an ingestion/replication protocol, right? And the first phase of that is the publish, and the second phase would be validating. So, and I'll talk about Ever in a little bit, but the idea behind validation is that if there's a schema attached to the message, we validate it right there. And there's a lot of value to that if you're doing a streaming platform or trying to bootstrap. Don't delay on validation. Validate as proactively as you can. And we'll talk more about that in a little bit. And then the last phase of the ingestion is ingest. And that will send it to Kafka transport, that will send it to Kafka. And this is just an actual class. This is the Kafka ingester. And you see like the publish, all it does, it checks to see if there's a Hydra Kafka topic parameter in the request metadata. And then if there is one, it's like, yeah, I want it. I want this request. It's interesting to me. And then there's a validate, and then the ingest that happens after that. And you can see here if it just basically sends it to the Kafka producer, if everything goes well. So this is all Akka. These are all messages in Akka, right? So they're all asynchronous. So you get a publish, he gets a publish, he replies back with a join or an ignore, and then sometime later down the road, he'll get a validate, and then the last message that this ingester will get is the ingest, and then he just acts on that. So that's what we call the ingestion protocol. So what about metadata? And I'll also put the slides available. I'll put them somewhere so I can send you guys. I'll put the link on so you can take a look at it later, probably slide share. So what about metadata? So what kind of metadata should we capture with these payloads that are coming in? I would say as much as you can, but you don't want to put too much burden on the producers, right? Because now it's an extra step for anybody who's producing data into the platform that they have to provide some type of metadata with the request as well. We have made a decision to always capture metadata at ingestion time. And I think it makes a lot of sense because it brings up automation. So you can do a lot of automation because you have the metadata already. And metadata, I mean, if it's a JSON payload, you're describing the fields, the types of the fields, if they can be null, if they cannot be null, or maybe ranges, that kind of stuff. And if you do that, Spark down the road can also use that same schema to build its data frame, build its data set. And we also use that same schema to build the table in Postgres. So the schema becomes the metadata layer on top of this whole string processing framework, all the way from ingestion to materializing the data in Postgres. And this is pretty much what we believe in, right? So if we have data and metadata, we can make more kinds of data sets readily available and easier to use, because it doesn't stop there. If you think about, again, this platform is meant to serve more use cases than just bootstrapping. You have data analysts, and if we have metadata attached to Kafka topics, then this whole thing, this whole ecosystem becomes searchable. They can search by keywords. They can search by documentation. They can search, they know. So it's not, one of the problems that we have with Hadoop today is that it becomes, after a while, it becomes a black box. There's all these tables, all these columns, all these views. You don't know what's inside. I don't know. It's like hundreds of them. How am I going to know, right? So as opposed to have something like this, that you can have a UI, you can have a portal, and then you can search. I want to know every topic in Kafka that has username attached to it. So I can search, and that brings back up. And for this, we're using Avro. I don't know if you guys are familiar with Avro, so I was going to talk about it just a little bit. Avro is back from the Hadoop days, it's a binary format to store data in Hadoop. And it seems to be becoming kind of like the de facto standard for Kafka and schema-driven messages in Kafka. And so why do we choose Avro? Number one, it's because the schema evolution capabilities behind Avro. So Avro is basically, it defines a record using a JSON schema. And the idea is that you can add fields, you can remove fields, and as long as they're compatible, you can evolve the schema. And it's really cool because now I can have a producer that's producing a message with schema 1, and I can have a consumer, like we talked about earlier, the picture of everybody being replicating from the same Kafka log, but they can be replicating using different schemas. As long as they're compatible, Avro allows that to happen. So we can have a long-running stream topic of schemas that are continuously evolving. And even if I add a column to my JSON stream, it doesn't break my clients, as long as they're compatible. And that's where a tool from Confluent called Schema Registry. So that's what I'm saying. There's a lot of support in the industry right now around Avro in Kafka. So there's a tool from Confluent called Schema Registry that basically makes sure that all your schemas are compatible. So right now in our data platform, all of our Kafka topics are Avro topics. And that's based on the Confluent Schema Registry. So they have a Kafka serializer and a Kafka deserializer implementation that's based off a Schema Registry. And the Schema Registry just basically makes sure that your schemas are compatible so that you can either produce with a schema or consume with another one, and you can have this long-running unified view of a data stream. And also a smaller data footprint. The topics in Kafka, the files in Kafka, and the file system will actually be a lot smaller than just JSON because Avro, it knows what the field names are, so it kind of strips all those out and only basically stores the actual values on a byte array. And it can actually do also compression, so you can do Avro with Snappy or Avro with gzip, and it really gets the file sizes a lot smaller. And then the other one, JSON friendly, like as opposed to protocol buffers or the other serialization frameworks that are out there, Avro works with JSON. You don't need to have a strongly typed object. You can work with JSON all the way from the beginning all the way to the end, which is important for us because our development teams at Pluralsight, that's what they're used to. So for them, it's almost a transparent experience. They're still producing JSON and consuming JSON. The only thing that they have to do now is create an Avro schema that describes the stream or that they're producing to Kafka. And like I said, there's a strong community support from Confluent, from the Kafka community, a bunch of open source projects around this. And there's a lot of tools. I haven't really seen a programming language that doesn't have a library for Avro. Java has one, Node has one, Ruby has one, C# has one. They kind of vary a little bit, but there's a lot of libraries out there that work with Avro. But again, if you do it right, and I quote right, Avro should almost remain an implementation detail within your platform. The only thing really that developers or producers should provide is the schema. Everything else, they shouldn't really be serializing messages at Avro or consuming Avro messages. It should be JSON or some type of other interchangeable format that's not dependent on a library like Avro. Okay, and then on the other side, so that's for ingestion, right? Metadata, Hydra, and then on the other side we have Hydra Spark. And this is the streaming, kind of the streaming protocol that we have going on right now. It's kind of the other side of the picture. So what is it? So what's Hydra Spark? It's really an abstraction on top of Spark data frames and Spark datasets, if you go with the Spark 2 language. And what we're doing, we basically model long-running data flows based on a source and a bunch of operations that kind of fit together. We're using a custom DSL because the idea is that we don't want anybody that needs to bootstrap a microservice to have to write a Spark job. But we also need to be able to configure it, change the name of the Kafka topic or the batch duration for the Spark streaming job, and that's all done via a DSL. And I'm going to show you an example a little bit. And it's also API driven. So there's a post endpoint, a RESTful endpoint, that anybody who has credentials to can post a DSL to or delete a DSL, stop your DSLs. And the DSLs, that's what they're doing. They basically get compiled into a Spark streaming job that runs behind the scenes and do basically what the steps of the DSL describe. So yeah, we're using the abstraction, and I have an example here. Hopefully it's going to work. Hold on a second. There we go. So that's what it looks like. I'm trying to make it a little bit larger. So that's a DSL. If you guys have not seen the syntax before, it's called HOCON. It's from typesafe config. It's like a JSON superset. It's very much like JSON. I mean, you could write JSON, but it doesn't have the quotes. It doesn't have the colons. You can use equal signs. So it's just more friendly. You can do include files. You can define variables. It's almost like a little programming language. So that's what DSL looks like. You have the transport element at the top, and then any Spark configuration parameters that you want to pass to the backend that will go here. And then you have your source. This is basically data flow. So here we have a Kafka, so the data is coming from Kafka. And then the topics that you want to, this is the name of the topic, the invoice. And then the format, we're talking about Avro, right? The format of the topic is Avro. We're using that Avro schema to read data from that topic. And then the start is basically the start offset. Do you want it to be start at the end or in the beginning, right? And if you do this here at the top, that makes this whole DSL a Spark streaming job, that streaming that interval at the top. So that's how you switch back and forth between if you don't do this, if you don't put that in there, it's just a Spark job. It runs once and then it's over. And mostly for the data teams. The data teams, they use it like that if they want to run a one-off export from Kafka into Postgres or from Kafka into HDFS. Run once and then be done. And then here are the operations. Filter by value, basically filtering is like a where clause, but using Spark terms, right? I mean, just basically filtering a data frame. And then this is the upsert. So this is the actual bootstrapping part right here, if you want to think about it that way. So it's a database upsert. So as the data is coming in, it will generate an upsert statement to the underlying database, in this case, Postgres. So we'll filter first, and then we'll just insert into the table. Okay, let me see if I can go back. Okay, all right. And then in terms of code, and this is open source now. I'll show you guys the link. Feel free to take a look, and we'll talk more about it in a little bit. But so you have the source. So we talked about like the source right before on the DSL. So this is basically a trait. And you see there's two methods, create stream, that creates a discrete stream in Spark, and also our create data frame, that creates a data frame or a data set. And that's what each source has to implement. Or in a checkpoint operation as well. This really only applies to commit logs. In this case, it's for Kafka mostly, because the idea is that you can have incremental exports out of this. So you run it once, and then you commit your offset. When you run it again, it's only going to give you the new messages, not everything, not the whole log. And then here. And then the DF operation, data frame operation, this is pretty much the only method that we should implement, and this is the transform. It takes a data frame, and it returns a data frame. So you can do whatever you want to do with it. You can filter out columns, that's kind of what that one does, or you can add columns, or you can save it somewhere. And I have some quick examples here just so you guys see what it looks like as well. And like I said, this is all on GitHub. So this is the Kafka source. And you can see like the different formats over here, the Kafka JSON format, the Evra format. These are the formats that we support right now. And you can see those, the create stream method and the create data frame method. And it's pretty cool. Like I said, it's all Scala as well. And it can be as complicated as a Kafka source, or it can also be as simple as a file source, right? I mean, you can basically, Spark, you can create a stream. Spark has a streaming capability out of a file, a directory. So basically, every time that there's a new file in a directory, we'll just run that stream again for you. And then just this one here, because this is the database upsert operation. So this is the one that actually does the bootstrapping, right? The upsert into a database. And this is pretty much it. This is the method. There's a lot going on behind the scenes. Like I said, you guys feel free to check it out. But that's pretty much it. That's the Spark code. And again, we decided to go in the DSLs because we want people to write that JSON or HOCON, send that to an endpoint, and just be done with it, right? And then behind the scenes, we'll either compile that into a Spark job. That's the only option right now. But we could also use Akka streams because now we have this abstraction layer, right? So the idea is that we could see, looking at this, looking at the invoice topic, we know it's a super massive topic in Kafka. So yeah, it makes sense, right? I mean, to run that in Spark. Or if somebody sets a streaming.interval to 1 millisecond, we know Spark can do that. So let's not use Spark to submit that job to, let's use Akka streams or Kafka streams. So that's the idea, that looking at some of the clues that we have in the DSL, we would be able to direct this job to the most efficient way to run it. Right now, it's not there. It's all Spark, but that's the idea. That was also the idea behind having this abstraction layer on top of the streaming framework. And then if you put it all together, it looks like this, right? So you have these services, these here on the production side. They all write messages or send messages to Hydra. We don't write to Kafka directly, and this is a design decision that we made in the beginning because we want Kafka to remain as an implementation detail behind the platform. We want to be able to change it if we need to, or I don't know, something else comes in, or a better solution may come in that's not Kafka. But we want to be able to change without affecting the whole company. And Hydra also adds more stuff like we saw, right? I mean, it adds like the Evra conversion, the schema conversion. It also does stuff like message validation. It's built on top of Akka, so it gets a lot for free just for that. It can be replicated. So there's more that we get from Hydra than just the gateway into Kafka. And we know it stores in Kafka at a minimum, right? I mean, it could go to different data systems as well, right there. And then on the other hand, on the other side, you have services like a customer service that wants data from those two guys. He will post the DSL to the endpoint that's part of Hydra as well. That will create a Spark job that will basically stream those topics, join or normalize, whatever, and it will materialize that directly into that bounded context. So Kafka becomes the source of truth for all the data that we're using to share across microservices like that. Like I said, we are on GitHub. Hydra Spark is actually open source right now, so you're free to check it out. You can check it out if there's anything you know how to do better. If you want to contribute, you're more than welcome to. We're actually in the process right now of upgrading the master branch of Hydra Spark is 1.6, Spark 1.6. We are in the process right now of upgrading to Spark 2. So that was a pretty big rewrite, just to kind of take advantage of all the structured streaming and the Kafka implementation. Because Spark 1.6 is Kafka 0.8, and Spark 2, they finally upgraded to Spark 0.10. And it's totally different. It's very different. So the majority of the refactorings were around the Kafka consumers and producers in the Spark code base. So we probably, next couple of weeks or so, that will become the master branch. Just so you guys know, like right now it's Spark 6, Scala 2.11, 2.10. The master branch will be Spark 2, Scala 2.11. And we're hiring. So if you guys are interested in data, if you love data, if you like Spark, if you want to work with these technologies, just reach out to me today or on Twitter. My Twitter handle is on the Scala Day schedule. Just reach out to me there and we can talk more about it. It's a pretty interesting project. It's very challenging, but it's a cool project to work on. And that's it. Thank you guys. If you have any questions, this is the time.
How do you handle invalid messages in Hydra? You said you have a schema that does validation.
Yeah. So the Hydra messages, they have a never schema that gets attached to them, and there's different ways that we match. Right now, the default behavior is that the topic name in Kafka will also match the name of the schema in the schema registry. So when a message comes in with a topic name, we basically use that to look up the schema in the registry, and then we validate the message at that point.
What if the message is invalid?
Then it goes to that letter queue. Two things happen. It goes to that letter queue in Kafka. So we know that. So the idea is that once the messages cross that barrier into Hydra, they don't get lost. Right? We don't just say, hey, we don't want it. And we also reply back to the client with a 400 error, saying, hey, our message is invalid, and here is why. And the expectation, even though that's not always true, but the expectation is that the clients will not just fire and forget. They would be able to react, right, somehow to the 400 and do something about it at that point.
When you chose Avro, was it like a greenfield situation, or did you already have a bunch of existing JSON schemas? And did you, what was the process of taking the time to convert everything to Avro?
That's a good question, actually, right? So it's a very contentious topic, actually, to talk about Avro and JSON schemas, because it does bring that overhead of having to create a schema, especially if you have a bunch of services we're used to producing JSON without worrying about structure, right? Now we're adding a layer, and when we're talking about schema, it kind of brings memories to databases. Now we have a schema going to be tightly coupled, and it's not, so there's a lot of, it was a greenfield, right? It was just basically a lot of research that I read in the Confluent white papers and why they decided to go with Avro, and really the problem that we're trying to solve of data automation and being able to do these things automatically, and just being able to discover the data in an automatic way. Avro is a really good fit for that, and it does kind of alleviate some of the typed or strong schema concerns with the evolution capabilities, right? Because it allows you to add fields. You can make every single field in your schema not required, so you can come up with a very permissive schema, though that may not be the whole point, right? I mean, you kind of want to stay somewhere in between. But so that's the idea, is that with Avro, we have a lot more leeway with how you define your schemas than a database schema, for instance, right? So that was kind of the process, just basically going through what we're really trying to do, and automation is a big part of this. I mean, we can't really bootstrap a JSON topic. How are you going to infer the schema from that? You could rely on Spark. I mean, Spark has a very good schema inference model, right? I mean, it will sample the result set, the data frame for you, and be like, oh, this looks like an integer, this looks like a string, this looks like a date. It actually does a pretty good job, but it doesn't work every time, especially if it's all nulls. We had a case like that, right? There's a bunch of null columns that was a string in the database, but Spark was trying to send that as a double for some reason. So that's when we realized, hey, let's just use the schema to build the struct type of the data frame as well. And Avro, it's really becoming as this metadata layer on top of everything. So Uber does the same thing as well. They're actually building their own implementation of the schema registry, the Confluent, using Avro, and they're also using the Avro schema to translate or convert like Avro files into Parquet files. So just the industry, right? Avro seems like the last year or so, Avro seems to be becoming like a first-class citizen in this kinds of environments. So that to us, that made a lot of sense just to kind of just go and do the same thing, because a lot of movement here as well. Any other questions?
Could you share what's the peak throughput of your system, like messages per hour, and what's the configuration? Like how much memory, how many instances, especially in Hydra?
Yeah, okay, so Hydra right now, it varies a lot, depends on the topic, on the time of the day, but we have anywhere from 500 to 1,000 messages a second, everything together. Hydra right now runs as a 3-node, it's AWS, and it runs behind an elastic load balancer, an ELB, and it's a 3-node for ingestion.
Sorry. Go ahead.
3 nodes, how much memory per node?
I don't, do you know, Dustin? No, I don't know. But they're not massive. So before, we started running Hydra as part of the data team in Pluralsight, and we were running one single Hydra instance on M3 large nodes, and those are about 8 gigabytes. So it's a very lightweight framework. It's not meant to be this beast. It's not meant to be Spark. It's really just about replication, right? I mean, handing data over to these other different systems. Hydra is about integration. It's about bringing these systems together in a way that's configurable. So you can, I think that's what it is. The M3 large instances are like 8 gigabytes of memory. And that's what we had it running. Before it became like a major product within Pluralsight, that's what we had it running under. Just one node, 8 gigabytes.
Hi, I'm interested in the execution aspect of this in terms of how many teams do you have working on this? You mentioned at the beginning of your presentation that with microservices, you guys you have one team that owns one service. How many teams, how many developers per team? Can they run the whole system on their own laptop, that sort of thing?
Mm-hmm. So the development teams at Pluralsight, do you know how many? 4 to 6?
Are they able to run this entire system on their own machine?
Yeah. So we have a Docker image for all of this,
Okay.
right? So they can, at development time, they can, but that's not the goal, right? We've been talking about, on the Spark side, supporting, because the whole idea behind a binding context, you want to own as much as you can, right? Both Hydra and Kafka are meant to be global, shared services for Pluralsight data, right? This data platform. But we have been kind of playing with the idea of allowing teams to basically materialize their own Spark context or the Spark cluster within their bounded context. And we're using like Elastic, EMR, Elastic MapReduce from AWS. We actually run a prototype to try to do that and see if it works, but that's the idea. So right now it's all shared. The Spark cluster is shared. The Kafka cluster is shared. Hydra is also shared as part of this global data platform, but there's some movement to at least federate or separate the Spark piece of it into their own bounded context.
So how do you guys, for instance, replicate data from between different environments so that you can solve certain problems in a dev environment versus a stage environment and so forth?
We don't. So we don't really replicate data between dev. We don't really have a dev environment at Pluralsight. It's whatever each development team is working with locally, right? I mean, that's the Docker containers that they have. And we do have a staging environment for Hydra and for all this other stuff. And that's pretty much, we basically use different namespaces for the topics. So that's kind of how we isolate the topics as well. So the topic is not just invoice, right? I mean, it's like engineering.invoices.sales, something like that. So the topics are isolated by name as well, by their namespace.
Great, thank you.
Mm-hmm.
I have a question on the Hydra. When you have the events, Hydra receiving the events, and you have to preserve the timestamp of when the event actually happened or Hydra has received versus when it is committed into Kafka. Mm-hmm. So did you have any challenges? Because we have a similar system, and we have challenges in treating when the event actually happened, the actual time versus when you committed. Mm-hmm. And it gives an illusion of, it happened later time than when sometimes it has happened.
So let me see if I understand the question. You're talking about the different dates between when an event gets received by Hydra and when it gets committed to into
yes.
Kafka? This is a good question. So before, and we stopped doing this, so when the first versions of Hydra, we were working with Kafka 0.8, and Hydra would actually add a timestamp to every message that would come in and put that in the key of the Kafka messages. But since we upgraded to 0.9, and it's actually using 0.10 now, Kafka, since we're just basically using that, whatever Kafka has at the timestamp of the message itself, that's what we're using. So we stopped using the two timestamps. We just rely on the Kafka timestamp for right now.
That's in 110, you said?
Yeah.
Oh, sorry, 010. All right, yeah. Thanks.
Mm-hmm.
So, hey, Alex, thanks. Great talk. We're on a very similar journey. My desire is to use Kafka as a source of truth also, and we've been using Spark for a couple of years. In batch mode, Spark, we've had like 0 issues. In streaming, we've definitely hit some issues with Spark. It seems kind of relatively immature, the streaming versus the batch. Have you hit, or are you aware of the bug where Spark streaming can't read from a compacted topic that's missing sequential offsets?
No, I haven't. Let's talk about it.
Yeah, let's definitely talk. That kind of rained on my parade a little bit.
Yeah, because that'll be good to know.
Yeah.
Because we do that now and we haven't had an issue yet. But maybe there's a corner case or something.
Yeah, okay.
Any other questions?
All right, guys, thank you.